Hello there, my name is Paweł, machine learning engineer at Roboflow, and today I'll be talking about building a visual search engine for your images. Before diving in, let's discuss what visual search actually is. This is the term to describe a piece of technology that lets you query a large pool of images, either with text, so queries in natural language, namely plain English, or with other images. Let's put it into context. Assuming that we have a directory of images that we don't know anything about apart from their presence, we don't have descriptions of the images, we don't have any tags, we don't know where those images were shot, we don't have GPS tags, for instance, but we want to find particular images that were taken in Paris. So with visual search system in place, we can simply query that we want to get pictures from Paris, and what visual search engine is capable of, it's going to retrieve the images that are relevant to our query, as depicted here. This is really nice, but let's see what visual search can be used for when it comes to practical applications. It turns out that if you are running an e-commerce, you may easily build a system to suggest similar products for your customers, but based purely on the visual appearance of the products that people were looking for. If you have a warehouse, you may build an inventory management system to locate items based on what kind of products people are looking for. If you have a production line, you may want to build the detection, quality inspection or defects finding system to ensure that the quality of your products in the manufacturing line is aligned with your expectations. If that's not enough to convince you that visual search is a thing, I will also mention that visual search is quite easy to integrate into existing systems because this is simply the evolution of a search that is already installed in various different systems around the world. And this is just a step up to involve also image modality into the search capabilities. The good news is that you may not really need to train any custom models whatsoever to have visual search system onboarded into your platform. And even if you do, it may turn out that you don't really need to retrain models over time because those are simply the ones that usually generalize very well when it comes to the tasks for retrieving the data from the pool of unstructured datasets. What's even better is that visual search systems usually effectively scales into millions of images. And what's even better is that you can build them with open source tools, including the ones that we built at Roboflow, which I'm going to illustrate in a moment. Let's start from the description of the problem that I'm going to solve with the demo. I must admit that I have quite messy phone gallery. Whenever I have some picture in mind that I would like to share with my friends, I need to scroll endlessly, ashaming myself. So if you don't want to be embarrassed in this kind of situations where you want to share some photos with your friends, let's see how to build a system to solve this particular problem. I've prepared the Jupyter notebook with some pieces of code that utilize our inference server, which is open source inference tool provided by Roboflow, and HTTP client for that server to make requests and get responses back. So let's import the client and initialize it and see what I have prepared in a directory of images for this. You can see that there are a few really nice photos here from various different places in the world, presenting really nice places to go to visit as a tourist. I can load all of those images into memory to be able to compute so-called embeddings. Now I would like to describe you briefly how this visual search works in a nutshell. You may know that images representation in the computer are very basic. We have just array of pixels, and for each pixel we have a color. This representation is really handy when it comes to displaying the image on the computer screen, for instance. But that's your responsibility as a human being and your neural system in your brain to bring some semantic meaning into what being displayed in the screen. However, if you wanted to build the visual search system, we usually want to retrieve information from a large pool of images that were never inspected by any human being or are rarely inspected by any human being, and we want to do it automatically. So we need to have a tool to build this semantic understanding, semantic representation of images in a computer. And hopefully there is a model which is called CLIP, which is able to produce this kind of representation, which we call image embedding. Image embeddings works in the following way. If you have two images that are very similar to each other when it comes to its contents, the embeddings, once we calculate a similarity operation on top of them, would indicate very high similarity versus in the situation where when you have two different images depicting very different visual phenomenons, the similarity between embeddings would be low. So let's see how to compute embeddings using the inference tooling. I have this very simple function that I just iterate over the images and use HTTP client to the inference server to send request with an image requesting to get the CLIP embeddings back. CLIP is the model that we will be using to produce the embeddings. So you can see that in a couple of seconds, I'm able to compute the embeddings for those 81 images that I have in a directory. If I display the embeddings to you, you will not see anything meaningful. This is just an array of numbers. I can even print it here. You can see just a bunch of floating point numbers, nothing really relevant for human being. But if we compute the similarities between each part of images and display it, you can see something interesting. This matrix that I'm just showing visualize the similarity in between each pair of images from my directory with yellow color indicating 100% similarity and dark colors representing lower similarity levels. You can see on the diagonal, this is a similarity of an image with itself, so it's obviously 100%. But having that similarities computed, what I can do is I can pick pairs of distinct images that are most similar to each other, which is exactly what I'm doing here in this function. And you can see that I'm able to retrieve automatically two different shots of the Paris Louvre Museum by night, and I can immediately recognize automatically, like without me inspecting the data, that those are similar images. The same with those two different shots of Dubrovnik city, which fans of Games of Thrones may easily recognize probably. And the same with other pictures, like here is the Louvre by night and Louvre by day photos. What I haven't shared with you so far is that CLIP is not only capable of producing embeddings for images, but also for text queries. And what's even better, those final embeddings, like produced from images and produced from text, are being possible to be compared against each other, providing meaningful results. What it actually means in practice is that I can create this query dataset function to compute embeddings of my text query and compare them against the embeddings I have already computed for all of the images. So let's see how it works in practice. I can ask for questions for images relevant for the query Notre Dame de Paris, and you can see that the first three images are basically the perfect match. First two are the pictures of that particular monument from the outside. The third one is the picture of this monument from the inside of the building. And then you can see that the search returns us also less relevant entries. Those ones are relevant for Paris, but not necessary for Notre Dame Cathedral. But you can also see that the results are being ranked based on the level of similarity with the query, with this top one being the actual monument, and the lower similarity entry results are less relevant to the actual query. So this is great. And you could see that I was able to compute everything required to build the fully fledged visual search system just in this amount of lines of code using our inference tooling. So that's already great, but we know that not all of our clients are really interested into coding, and it may take some hassle to set up the whole processing environment, pull the data, and run the processing properly. So what we have built is the batch processing capability in Roboflow. We have built both our cloud-hosted version and the self-hosted version that you can run on your computer. Let's see how the batch processing in the cloud looks like, and then we will illustrate how to run it locally. Chandler already told you about workflows. So this is our computer vision application builder that you can use to solve your problems with computer vision models. And I have built the workflow that computes clip embedding. So exactly the same procedure as I have coded in the notebook. With batch processing in the cloud, I can simply navigate into Roboflow panel. Under deployment section, I can click batch jobs to spin up a new job. I'm selecting the workflow, which is like clip embeddings. And now I'm able to just drag and drop images. And I have this directory of raw images, 81 images here. I just click create batch job, and everything required to build this search index is going to be done automatically without any intervention from your end, without any coding. And at the very end, what you can do is just click this export button that you can save all of the results from the processing. We are not going to wait until this processing finishes, because this is asynchronous job that requires spinning up compute machines and then processing the data and saving it properly in our backend. I'm going to present to you the ability to run the exact same processing locally in your computer. So we have inference CLI, and in inference CLI, we have the command which is called inference workflows process images directory, where you point input data, where you also point where the outputs should be saved, and you specify the workflow that should be running against your data. If I click enter, you could see that the processing is being up and running. We have 81 images to be processed, and really quickly, after a short while, we have results delivered. That's really great. That's also what's going to happen in this cloud processing that I have started. But you may also admit that 81 images is not an impressive number. To provide more tangible data, I prepared a gallery of images which has now 50,000 entries nearly. So let's see how long you would be processing this data locally. So if I run the same command just against this larger pool of images, as you may expect, the progress bar would indicate slightly longer processing, in this particular case, like 30 minutes. We are not going to wait until this finishes. I have already computed everything for you. So coming back to this notebook, I'm able to build an index of images using Facebook AI search similarity vector database to effectively be able to create search API That I'm going to present in a moment with frontend, such that we can really nicely play with this visual search system that I have just built. So I have this function to build the local index. What it's going to create is a file with index of embeddings. So basically all of the embeddings that I have shown you being computed in memory are dumped into this file that can be loaded in my API. And I also provided some metadata with very simple mapping in between position in the index to the name of actual file to be displayed later on. So that's basically it. But you must know something about this processing. Like, it was already very long, I showed you, and all of this data, like this 50,000 of images, is actually like 10 gigabytes of data. If you do anything in your work, usually you would need to pull this data from a central location, like cloud storage, into your computer, then do the processing, hoping that everything runs smoothly. And only after that, you are able to get the results you are interested in. We built this batch processing to be able to handle large volumes of data and to handle it in a very nice and convenient way. So if you work in a company that has the data stored in cloud storage, what you can easily do is you can generate the pre-signed URLs for all of the images you want to process. So I generated this kind of images. You can see, like, I can just click to get the contents of the image. And we have our inference CLI also built to interact with batch processing in the cloud. And utilizing that options, the commands that I'm just showcasing here, you can ingest this large directory of images stored in your cloud storage to our system, easily process it, and then just export the data. And I'm not going to run the whole procedure now because it's also going to take some time, because that's a large pool of data at the end of the day. But I can build the exact same index that I was building from my results obtained locally and use it in my application as well if I wanted to have a drop-down replacement. Long story short, whatever experience you have here, like playing with the data locally, you can very easily transform it into the experience of running something in production grade environment where the volume of data is large and you need to process something in a systematic and very arranged, sorted out way that is required by your company. Without further talking about the batch processing, let's see what is the final result of our demo. We are building images index to be inserted into our search API. And on top of this search API, I have built the front-end app that is capable to interact with this API, requests, and visualize the response. Just remember, I have indexed 50,000 of images. I don't really know what the contents of each and every image is, but let's see what we can explore in the data set. Recently, I was in London, so let's see how London looks by night. So if I hit a search button, you can see with very small latency, almost imperceptible, almost not possible to be perceived, you can get really nice results illustrating London by night. I'm not really sure if all of them are actually from London, but at least some of them looks like. I'm from Poland, so let's see what kind of images from Poland were in our gallery. So let's see. So this is definitely Poland, Krakow. Coincidentally, this is the city where I live at the moment. I really like it. And you can see that we have pretty nice monuments here in Poland, but we can search whatever we wanted. We can, for instance, try to search for castle in the mountains. Let's see what's going to happen. Yeah, I can see from the results that they are quite relevant. How about horse and either, right? You can see that I'm getting quite good results, which are, by the way, quite nicely looking photos. And I've also told you that not only you can query by text, you can also query by another images. So I can just try to find out the images that are similar to this Notre Dame Paris image. And you can see that we have plenty of different shots of this particular monument from various different perspectives.